In the previous sections, we only used a rectangular domain, but what if we wanted to have a domain of a different shape? A quick answer to this is that we can always embed a finite region inside of a rectangle, and then we just define a new function that matches the given function on the initial region and 0 everywhere else. And while this works as a theoretical answer, it doesn't help us in any practical sense. So to get to a more practical solution, we're going to consider two types of regions. Some books call these Type 1 and Type 2 regions, but it's not that important of a distinction. The idea is that we're looking for regions that can be completely covered by thin connected rectangles in either the vertical or the horizontal direction. This corresponds to the thin slices we made in the previous section. Our basic goal is that we want to make sure those slices make sense. This first example is a typical example that can be covered using vertical rectangles. The key features here are that there is a lower function and an upper function, and that the region is bounded by constants on the left and the right. With these bounds set, you can draw in connected vertical rectangles and cover the whole region. This also gives us the information we need to set the limits of the integral. The main principle is that your integral should always be understood as lower to upper. The inner integral is a dy integral, and the bounds for that are of the form y equals something in terms of x. For the dx integral, the lower constant is a, and the upper constant is b. We've been repeating the phrase connected rectangles. This next example shows how you can get a failure of this. On the right side of this region, there is no way to cover both tips with a single rectangle without also covering areas that are outside of the region. The only way to cover just the parts that we want with vertical rectangles would be to have two disconnected pieces at the same x position, or use more advanced techniques such as dividing the region into multiple pieces. However, if we use horizontal rectangles, we can sidestep all of this. Horizontal rectangles correspond to integrating x first. The lower curve is on the left, and the upper curve is on the right. Notice that these are functions of y, and not functions of x. And the lower and upper constants are now in the y direction. We can see that the rectangles cover the region, and this gives us the setup for the integral. Notice that the order of integrals has been swapped to dx dy. This is very important. There are some regions that can be covered by either type of rectangle, but there may be practical reasons to prefer one over the other. Consider this triangular region. It's not hard to see that this can be covered with both horizontal and vertical rectangles. However, it turns out that if we use vertical rectangles, it will be slightly more complicated. To understand why, we have to think about the functions involved in defining the boundary. The lower curve is straightforward, but the upper curve is actually two separate functions. This means that when we set up the integral, we're going to have to break it into pieces. Sometimes this is a necessary step, but in this case it can be avoided by using horizontal rectangles instead. This arrangement gives us one lower function and one upper function, and this means we can set up the integral as one piece. I strongly recommend that students graph the region to help them visualize it. There's too much going on to try to keep it all in your head. We're going to work through example 11.3.3. We're going to set up the integral using both a dx dy and a dy dx integral to give you more exposure to that process. The full calculations are in the book, so we won't spend time on that. We really just want to focus on setting up the integrals. Here's the region of integration. For the first time through, we're going to integrate with respect to y first. This tells us that we will be looking at vertical boxes and that the limits of the inner integral will be of the form y equals something. If we look at the graph, we can see that the lower function in the y direction is the line y equals 0, and the upper function is the diagonal line. By doing a quick slope-intercept calculation, we can get that the equation for the line is y equals 3/2 x. And that sets up our inner integral. For the outer integral, we simply look at the leftmost and rightmost parts of the region. The leftmost is at x equals 0, and the rightmost is at x equals 2. Now let's look at the other direction. With the x integral first, we are looking at lower and upper functions to be of the form x equals something. The upper limit is x equals 2, and the lower limit is the diagonal line again, but we need to write it in the form x equals something. In this case, it's easy to get the equation x equals 2/3 y for the lower limit. Then the y limits are y equals 0 and y equals 3. And now we can set up the integral. Sometimes the region of integration will be implied in the limits of the integral. In these situations, it's helpful to sketch the graph of the functions in the limits to help you visualize the region correctly. This is especially important if you end up swapping the order of integration. You usually will not be able to do that without having a graph of the region. There may also be times when the integral itself is harder to integrate in one order compared to the other, and you won't necessarily be able to determine this in advance, so you may simply have to set things up and see what happens. One last observation for this section. For integrals over rectangular regions, we had a formula that gave us the average of the function on the region. The same equation holds for general regions. The function a of r is the area of the region, which used to be a rectangle but now can be anything. In some cases, you may have to integrate to find the area between the curves. However, if the region is a known shape, such as a triangle, a rectangle, or a circle, you may be able to use geometry to calculate the area instead of setting it up as an integral. As much as possible, you will want to find ways to simplify your work instead of blindly following a fixed process. This section expands our capacity to work with double integrals, which will help us in the coming sections. Make sure that you do the exercises to get enough practice with these integrals, as they are only going to get more and more complicated from here.